Today we are discussing about compression members. They are the members which take compression. Okay, so there are elements of a structure that take tension, and there are elements of structures which take compression. Okay, so the basic examples for elements, not just the materials, not just the ingredients or anything, elements. Okay, elements which take compression are columns, struts, pedestals, etc. Okay, these are some typical examples. Columns are the main compression members that we use in buildings. In every building, every main or massive building or an above average structure building, there will be columns. On the columns, from the foundation, there will be columns, and on the columns we will be structuring on all the beams. Then on that beam we will be constructing slabs. Then again we will continue that columns upward till the end of that building. Okay, so columns, we have all seen that. Okay, strut is a compression element which will be used in truss. These angle sections or L sections, etc., I sections, etc. That elements which take compression in the truss is called struts. Okay, pedestals are basically columns but very less length. Height will be too low, 0.5 meters, 0.3 meters, 0.7 meters, etc. Okay, so basically we are continuing on columns and we will take it up for the design. Okay, so columns are just a lengthwise structural element which takes compression mainly. Okay, so this is a typical column. Its cross section can be rectangular, can be square, can be circular. Okay, so as obviously as per our topic, we are only concentrating on RCC, reinforced cement concrete columns. Okay, so there are rectangular, square and circular columns, cross sections on columns, and based on the requirements we will be deciding on which type of cross section we need. Okay, and on this columns itself we have two types of columns. They are short columns and obviously long columns. Okay, and the part with which we decide a particular column is short column or long column is a ratio. Okay, it's similar to one-way slab and two-way slab in slabs. Okay, you have a ratio, and the ratio is L effective by least lateral dimension. Okay, and this is the deciding ratio. You know what is L effective? Effective length. Effective length of column. Okay, if suppose there is no constraints, nothing is given as an extra information, you can just take the length of column as L effective. Okay, if this is the length, just the length given, and if nothing else, no other information is given to you, we can assume this L effective as equal to L. Okay, in some other cases, in majority of the cases, you will be given a particular condition. Suppose this end, one end will be fixed, one end will be rotational, one end rotation is the straight. Okay, but there are many support conditions, as in beam, simply supported, cantilever, fixed, etc. Other end can be fixed. Likewise, two ends, there can be various types of end conditions, support conditions. On that basis of support condition, we can decide L effective from IS 456. IS 456, page number 94. Okay, so there is a table in page number 94 that you can refer with respect to support conditions at two ends, you can calculate L effective from the given L. The L will be given obviously in the question. You can calculate this L effective. It's a ratio. It's maybe 0.7 L, maybe 0.5 L, okay, 0.7 L, etc., 0.65 L, etc. So from this table you can take up the L effective value. And least lateral dimension is obviously, as the name indicates, it is the least of lateral dimension. Obviously for circle it will be this dimension. For a square it can be same, right? So same. For rectangle it will be the least dimension is this lateral dimension. Okay, for this rectangle it will be, this direction will be, this length will be the least lateral dimension, that's it. And if this L effective by least lateral dimension is less than 12, it is short column. And if this L effective by least lateral dimension of a particular column is greater than 12, it is long column. Okay, that's it. And the reason behind we are dividing this as a main classification, because as the length increases, if suppose this is a long column and this is a short column, okay, as the length increases, there are chances of having buckling. It is a failure mode. Okay, for example, this pen, this marker is cannot be fade, like it cannot be bent by just applying compression. But if suppose if this marker is of this much length, if I only apply, even if I am only applying compressive force, it can bend like this, right? You know that any long element when compressed, if it is sufficiently long, it can buckle. That is called buckling. Failure of this, that is a failure. So in long columns you will be having extra calculations to reduce the chance of buckling, but in short column we are not considering buckling. We don't expect a short column to buckle because the L effective by least lateral dimension value is less than 12. Okay, so that's it for the main introduction. Rest of the introduction will be covered, we'll be talking about in the coming numerical problems, design problems. Okay, so we'll continue on a problem. So this is the question. You have length of the column to be designed as 3 meters and size is already given. That may not be always the case. 400 by 500 mm size. And factored axial load, not just the axial load, factored axial load, that is, it is already multiplied with 1.5. Okay, we usually find factored bending moment by multiplying the given bending moment with 1.5, right? So in here you don't need to multiply with 1.5 with anything, axial load. If it was just axial load, you would need to multiply this value with 1.5. In here you don't need to, because there is this given as factored axial load. And M20 and FE450, assume it as a short column. Okay, so we have the details. Now we will start design. Okay, it's much easier to design a column than any other RCC structural elements. Okay, it's much easier because all the details are in the IS code. Okay, so we will start. We have FCK 20, FY 415, factored axial load 2800 kilonewton. Okay, so we have So now we need an equation to calculate directly the area of steel, because we don't need to calculate the size, we have the size. We are just writing right into the reinforcement calculation, AST calculation. Okay, in this case ASC, because it is compression in column. Okay, so we are calculating ASC. So for that you have page number 71 in IS 456 and refer. We have an equation called PU is equal to 0.4 FCK plus FCK AC plus 0.67 FY ASC. So FCK we know, FY we know, PU is factored axial load. Okay, 2800 kilonewton, and AC is area of concrete in the column. Okay, and ASC is area of steel. Area of steel is ASC and AC is area of concrete. Okay, so we have the values. Now we will calculate ASC from this. So PU is 2 into 10 raised to 3 is equal to 0.4 into 20 into 400 multiplied with 500, because the cross section is 400 by 500. There is an exception. What is the special case? There will be AC in here, right? If suppose there are 4 bars like this, you need to subtract this area ASC from this dimension 400 by 500. This is the total dimension. To get the area of concrete, you will need to subtract the area of ASC from this value, right? So 400 by into 500 minus ASC, that is area of concrete, right, plus 0.67 FY, that is 415 multiplied with AC. So the only unknown is ASC here and here. You just need to take out ASC from this equation by rearranging and calculate. There is 4,000 4,443.621 millimeter square. Okay, so from this value you can calculate AC value, right? This is AC, 40 into 50 minus this value, you will get it as okay. So this is area of concrete and area of steel in the concrete. Okay, so next step is just calculating how much bars that you will be having. We are just going forward with this value. Okay, this value is not much of that important. This is important. Well, next one is number of bars. As in beams, you won't be calculating any. As in slabs, you are calculating spacing, but it is similar to beams. You will be calculating number of bars and distributing with the number of bars. So number of bars will be equal to 4443.621 divided by, that is ASC, by single bar. We are assuming 32 diameter bars. Okay, so pi by 4 into 32 square. Okay, so you will get the value approximately 5 point something. Okay, you will round it into 6 number of bars. That means it will be like 1, 2, 3, 4, 5, 6, the longer side. Okay, this will be the approximate arrangement. Okay, so now you need to calculate how much ASC are we actually providing. We have gone through this. Okay, required is 443.621, but as we are providing 32 mm dia bars of 6 numbers, what is the actual? That is just ASC provided is equal to 6 into pi by 4 into 32 square. That's it. Okay, 6 numbers, that is 4825.49 mm square. So we have ASC provided as 4825.5 mm square. So now on we will be using this value for ASC. Okay, and we have in page number 48 of IS code the details of minimum reinforcement, minimum ASC and maximum ASC. Okay, so that is minimum ASC is page number 48. Minimum ASC is 0.8% of total area and maximum ASC is 6% of total area. So we need to be sure that this value is in between this value, in between 0.8 and 6%. Okay, so we will just calculate percentage of steel provided, that is equal to ASC provided divided by gross area or total area, that is multiplying these two values, that is 4825.5 divided by 400 by 500, that will give you 0.024. Okay, so for converting it into percentage you will need to multiply with 100 obviously. So into 100, that is 2.41%. So if we compare this percentage of steel provided value 2.41 with these two values, therefore it is safe. Try to write as a sentence. Okay, we are just passing through. Next one, check for short column. So we have started designing it, assuming it as a short column, but we want to be sure that after this much information that we have, we want to be sure that it is a short column. Okay, so check for short column. For that we will need to find that ratio itself, L effective by least lateral dimension, right? So this ratio is known as slenderness ratio. Please keep in mind, slenderness ratio is this ratio, and L effective, as we said earlier, in this question we haven't given any extra information about any support conditions or contact conditions of two ends, right? So we will take L as L effective. In this case, L is equal to L effective, right? That is 3 into 10 raised to 3 in millimeters. Least lateral dimension is what? 500 and 400, that is 400, right? So we have it as 7.5. It is less than 12. Okay, as slenderness ratio is less than 12, column is a short column. So that was check for short column. There is one more check. Check for eccentricity. So eccentricity is actually the distance from center of available area. How much distance is swayed for a particular force from center. Okay, for suppose if this is the column, this is the center line. Suppose this is the force acting point, this distance is called eccentricity. Okay, so you need to have more eccentric flexibility for a column. Otherwise, if slight variation of forces occurs, it will be failing. Okay, so that is the condition. We are checking for eccentricity. Okay, and the equation is E minimum, that is minimum eccentricity. We don't have any maximum value. You need to have at least this value, and the equation goes like this: L by 500 plus D by 30. L is effective length and D is least lateral dimension as an L by D slenderness ratio. Okay, so you need to check, as this is a rectangular cross section, you need to check both for both direction eccentricity. If suppose the cross section was square or circular, we don't need to do that, but in case of rectangular we need to check for both 400 and 500. Okay, so if this is the XX direction, E minimum is equal to 3 into 10 raised to 3 by 500 plus D is 400 by 30, that is 19.33 mm. Okay, so this is the minimum eccentricity required. So how will you calculate the comparing value? What will be comparing with this value? We will be comparing with value with 5% of lateral dimension. That is 0.05 into 400, this value. Okay, that is 20 mm. Okay, as 20 mm is greater than E minimum, it is safe. Okay, with respect to x axis. In next one, y axis. Same thing, E minimum is equal to 3 into 10 raised to 3 by 500. 500 is in the equation, plus the next one, this direction, 500 by 30. You will get something 22.3 mm. 5% of lateral dimension, that is 0.05 into 500, that is equal to 25 mm. Same condition, as 25 mm is greater than or more than E minimum, that is 20.3, it is safe. Now we are getting into design of lateral ties. Okay, lateral ties same as stirrups or shear reinforcement in beams. Same concept but in columns. Okay, so lateral ties will be like this, or it can be there can be a connection like this also. Okay. Okay, these are lateral ties. If this is the column, this is the main reinforcement, and these will be the lateral ties. Okay. Right. So in page number 49 you have the lateral dimensions or dimensions of minimum and maximum spacings of this particular lateral ties. Okay, and one more thing, we are not calling it as spacing, it is called pitch. Okay, so pitch is the distance between two consecutive elements of lateral ties. Okay, same concept, spacing is same as spacing, okay, but we just call it in a different name. So in page number 49 you have a clause with all much details, as in lateral ties are much won't be taking or accounting for much of the loads because we are only considering axial loads, right? So shrinkage forces or temperature forces just will be considered for lateral ties. Okay, so it can be of minimum value. Okay, so moving on, diameter of lateral ties shouldn't be less than, as in page number 49, 1/4 of main reinforcement, that is 42, right, and 6 mm, that is the bottom point. It shouldn't, in any case it shouldn't be less than 6 mm, and it shouldn't be less than 1/4 of largest of main bar. Okay, so in this case it was 1/4 into 32, that is 8 mm. So our reinforcement will be 8 mm diameter. Okay, so 8 mm diameter. Now next one, pitch or spacing. Okay, so as in the same page, the pitch shouldn't be greater than least lateral dimension of this column, that is 400 mm. Next one, 16 times dia of largest longitudinal bar, that is longitudinal bar is 32 diameter, 16 into 32, that is 512 mm, right, or 300 mm, least of this value. So as you can see, it is 400, it is 512, and 300 will be the maximum pitch. So you will just assume 8 mm diameter bars with 300 mm spacing. Okay, so 300 mm. So provide 8 mm dia bars with 300 mm spacing center to center, that is distribution lateral ties. Okay, so you have designed main reinforcement bars as 32 5 bars, 6 numbers of 32 5 bars, and ties are 8 mm dia at 300 mm center to center space. Okay, so this is how we design a simple short column. Moving on to the next one, So this is the second question. All the relevant informations. Axial load is 1000 kN, length is 3 meter. Again, column is effectively, there is the new condition with the ends. Okay, this is important. Column is effectively held in position and restrained against rotation at both ends. Okay, this both end is to be noted, because if it is just in one end, it would have been different. Okay, as in, you should refer page number 91. And restrained against rotation at both ends, M20 and FE450. As you can see, you have not been given any dimension of the column. Okay, so you have to design the dimension, then move on. Okay, so you have to work on more. Okay, so the same thing, actually there is no very little work to do. It is actually kind of simple with respect to eccentricity and all. Okay, so the previous one was a rectangular one. For our comfort convenience, we will be making this one as a square one. Okay, because square one will be easier to check for eccentricity and all other factors. Okay, square one is this cross section of our designing column. We will be deciding on the dimension. Okay, so the same equation, PU is equal to 0.4 FCK AC plus 0.67 FY AC. Okay, so for the time being, we will assume this square cross section dimension as capital D. Okay, so we know FCK is 20, FY is 415, PU is equal to, this is just the axial load. So we need to multiply with 1.5 factored axial load is PU. So 1000 kN multiplied with 1.5, that is 1500 kN. Okay, and AC, area of concrete. So if you are assuming as D, gross area will be equal to D square, right? Okay, and here is the point. We are assuming that, assume AC as 1% of gross area. Okay, so gross area is D square. We are assuming that AC is 1% of D square. Okay, so 1 by 100 into D square is the AC. Okay, and what will be AC? The area of concrete will be the remaining. Okay, we used to subtract this part from gross area in the previous one, but in this case you can write it as 99 by 100 into D square, right? Adding these two, you will get D square. That's it. Okay, no further explanation in like it. So we substitute these three values into PU. Okay, so 1500 into 10 raised to 3 is equal to 0.4 into 20 into 0.99 D square plus 0.67 into 415 into 0.01 D square. From this you solve the equation and find D is equal to 374.4 M. Okay, so obviously as it is concrete, we will approximate it into, round into the higher value. We can round it into 380, but for the easiness of cutting formworks and all, we are approximating into 400 mm. Okay, so dimension of column is 400 mm. Right. And what will be ASC? ASC will be is equal to 400 into d square, right? 1 by 100 into 400 by into 400, that will be 1600 or 1600. Now the next step is obvious. We just calculate number of bars. And here we will just take assuming 20 mm dia bars. Okay, so 1600 divided by pi by 4 into 20 square, that will be 5.09 something. You will round it into 6 numbers. Okay, so how do we select or assume this diameter of longitudinal bar? That is based on this number. Okay, so for square one, 4 is easier, right? Always 4 is comfortable, and 6 is okay. We can handle 6. And for rectangle also, 6 is advised or 4 is okay. 4 or 6 is advised. If suppose this number we are getting here is more than 6, you will increase the diameter. So number will come down, right? As a denominator, if it is 32, it will be like 3 or something. Okay, so we want our number of bars to be 4 or 6 in case of rectangular and square. But if it was around, it was circular cross section, 6 is a nice number. Okay, so we don't actually go for an odd number, we go for an even number. Okay, 6 is always advised for number of bars. 4 is also okay for square reinforced, square cross section columns also. Okay, so that's why we selected 20. Okay, so when we are doing a problem, actually designing a column, you can assume it as 32 and then carry out the calculations and get it as 3, then recalculate 20. Okay, it's okay. It's actually we will know that you have put down the effort. Okay, so it's okay. So right now it is 6 bars of 20 mm diameter. Okay, so main. So before that we need to check for minimum and maximum AC. Okay, that was 0.8% to 6%. This was minimum AC and this was maximum AC for any column reinforcement. So you need to have percentage of steel provided, that is equal to, we have provided 6 numbers of pi by 4 into 20 mm dia bars divided by total area, that is 400 by 400. Okay, you will get it as 1.18% into 100 here. Okay, so 1.18%, it is between 0.8 and 0.6. Okay, so hence it is safe, right? So as a result, provide 20 mm dia bars. So provide 6 numbers of 20 mm dia bars. Okay, so next step is actually the same as previous one. Check for short column. Okay, and check for short column is slenderness ratio L effective by least lateral dimension L effective. Here this term comes into action as in page 91 from the table. With this condition you can take up the value as 0.5 L divided by least lateral dimension is 400. So 0.5 into 3 into 10 raised to 3 by 400, that is equal to 3.75. Okay, that is obviously less than 12, hence next one is check for eccentricity. E minimum is equal to L by 500 plus D by 30, and that shouldn't be greater than 0.05 D, that is 400. So in this case, that is a square section, we don't need to calculate x's and yy directions, just substitute D as 400 and L as 3 meters. Okay, so 3 into 10 raised to 3 by 500 plus 400 by 30 shouldn't be greater than 0.05 into 400. So you will get this value as 19.33. It is less than this given value, that is 20 mm. Hence safe. Okay, so that is the second condition, and we are moving on to lateral ties. So for lateral ties, diameter of bars, we have two conditions, right? It either the greatest of 2 and second one is 6 mm. Okay, in no case it should be less than 6 mm, or 1/4 of largest longitudinal bar, that is 1/4 into 20, that is 5 mm. So we will select diameter of bar minimum value as 6 mm. So diameter of bars shouldn't be less than 6 mm. So assume it as 6 mm, right? You can take assume it as 8 mm also. It's okay. And pitch is equal to, it shouldn't be greater than, first condition is least lateral dimension, that is 400 mm. Next one, 16 times largest is value longitudinal bar, that is 16 into 20, that is 320 mm or 300 mm. So least of this value, that is 300. Okay, so you need to understand the difference. It is maximum value, that's why we took the bigger value. It is spacing, we don't want to increase spacing, so we will be taking least value. In this case, diameter, we don't want to decrease diameter, that's why we are taking the largest value. Okay, so we'll design it as provide 6 mm diameter bars at 300 mm space or pitch, center to center. That's it. That is the design, and you can calculate. You have calculated this, and you just need to provide a detailed diagram with these values. Okay, tidier one. This is 6 mm dia, 300 mm center to center spacing. This is 6 numbers of, this will be 2 more to be added, 6 numbers of 20 mm dia bars. These two details should be written here also. Okay, 400 mm. That's it.